All right, so this is going to be the first of my live classes on data analysis. And so I'm going to have an example of a set of data that you can relate to, which is test scores, of course. And then I'm going to show you how to conceptualize what standard deviation actually means, and how we use it in displaying our data and thinking about our data. So this course I've stripped down to the barest of bones so that we can do it remotely without putting too much pressure on you guys to learn everything yourselves, and also not too much pressure on me to have to video every single thing and expect you to watch all those videos. We're not doing that. I'm going to give you the absolute only stuff that you need to know and nothing more. That's it. The people who are in the meeting right now, you can be free to shout out at any time. I won't necessarily be able to see you while I'm showing the slides. So just if you want to be heard, just unmute yourself and talk to me. Okay, so let's start. I'm going to present my slides. So present here. Okay. So here, so imagine that I have two classes, and these I gave them both the same test. So let's say this is my AP Bio class, right? I've got two sections. I've got a morning section. I've got a afternoon section, and I gave them both the same test. And I look at these two test scores, and to me, they look kind of different to each other. My question to you is, like, if we were to describe the difference between these two results, how would you describe them? Does anyone want to give it a crack? You could type your answer, and I'm looking at the chat now. How are they different from each other? Give you a moment. So it looks like, so Jemima thinks that the PM has a higher average. We actually haven't calculated that, so we don't know. But there definitely are higher scores in the PM class. There are also lower scores in the PM class. So we could maybe describe that the range is different, right? The way that I would look at these is that, to me, the AM class looks a lot more consistent. They did consistently not so great. And the PM class is all over the place. And right away, as a teacher, when I see a result like the one on the left, the AM group, that to me tells me that, like, I messed up, right? It seems like something that I did, like, it's consistently, the class is struggling consistently. Although everyone passed, so that's pretty good. In the PM class, there's hundreds, we're all over the place, and everything in between. So I'm actually not really sure what's going on in that class. It might not be, there could be random reasons why those scores are different. And so Jemima said that she thinks that the average of PM is higher. Let's actually find out. I'm going to show you how we can do that in Excel. So I'm going to show you these data in Excel. And it's going to be very similar in Google Sheets. So just give me a moment. Here is my Excel. So here's a table, and I'm going to just show you a couple things about Excel here. So this is formatted in kind of a messy way, and so I kind of want to organize everything first. So what I'm going to do is I'm going to do Command or Control A and select the entire thing, the entire sheet with everything on it. Sometimes when you do Control A, it kind of guesses where all your data are, and I have to hit Control A again or Command A again, like everything. Now, when we go up here, I make sure I'm censored vertically and censored horizontally. Now everything's all lined up. That looks kind of nice. That's this area here. Also, oh, whoops, I put my averages here already. Oh my God, I gave it away. So I also want to make my data, I want to put my data in the table. So what I'm going to do is I'm going to select my data. And then over here, there's this area that says borders, and I can select all kinds of borders. So I want to go with all borders, like that, and then I can have my averages here. I'm going to show you how to take an average in Excel. Whenever you want Excel to do math for you, you're going to hit equals. That means you want the cell to equal something. And so if I wanted to equal this number plus this number, I could click on D3 and then type plus and then click D4, and that would be the sum of those two numbers. So what I'm going to do to take an average, I'm going to do equals and actually write the word average. And then it's asking for all the numbers to average. And so I'm actually going to click and hold it down and select all the numbers that I want to average. And so it's selected D3 colon D12. It's D3 to D12. I'll close my parentheses and hit enter, and it actually calculates it for me. Now I could do the exact same thing again over here, but that's too much work. I don't want to do that. So see how it says 71.5 here, but up here it says average. That's because this is the formula and this is what it's calculated. That what's cool about this is that it's always calculating this number. If I change the 77 to 1,000, hit enter, it's going to change my average. It'll update the number with what I'm typing. In the same way, if I copy and paste a formula, it will transpose that formula over. Look, right? See that little lower right-hand box here, this little green square on the lower right-hand corner? If I go hover over it and my cursor becomes a cross like that, I can drag it over. It'll copy and paste the formula and give me the number. Now, it's not copying the number, right? These are calculating this average. If I double click on this is calculating the average of these numbers. And their average is actually the same, the mean. For the median, equals median is the function for median. You can open up the parentheses, select all the numbers that you want to find the median of, and the median is 72. Now I can type that in again, but I'm actually going to copy and paste my formula. This works because it's all lined up. It's the same relationship. Okay. And then the mode, we can just see what the mode is. The most commonly occurring number is 77 here and 77 here. The mean, median, and mode are actually all the same. So if we are describing just the middle of these data, the middle is the exact same. So I want to go back to my slideshow. So you guys know what mean, median, and mode are. I'm not going to really spend a lot of time on it, but I will give you these slides. You'll have them. And so one of the ways we describe data is with these. We use descriptive statistics so that we can kind of get a general idea of the data. Because right now I'm showing you how many kids in each class. I'm showing you like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm sure 10 kids in each class, right? If I had data sets where each group were not 10, if it were like 100, then it's really hard to get a feel for what's going on in the data just by looking at all the numbers. We need these kind of summary things to see what this trend is. But in this case, the central tendency, the trend of the middle is the exact same for both these data sets. What's actually different about them is not the middle, but it's actually how they're distributed, how they're spread apart. These AM data are more tightly grouped together, and these are more spread apart. And so that's what we're going to use to measure. So you might know of range already, right? Range would just be the difference between the highest and lowest number, right? But we're going to use something called standard deviation, which doesn't just describe the difference between the extremes of maximum and minimum. It's going to describe generally how spread apart the data are from the middle. And I'll show you what I mean. So this is dispersion statistics. So, or spread, that's why I have this as spread here. That's standard deviation is written as SD for standard deviation, or S, or the lowercase s in the Greek, sigma, lowercase sigma. And basically all I need you to know with standard deviation is it's the average distance that each point is from the middle. So for our data here, it would be, the average for both was, I believe it was 71.5 was the test average. The standard deviation is to say, on average, how far is a given student away from that middle number. I will never make you do this math, but just for those of you who are interested, this is actually how it's calculated. And it's calculated a lot like an average, where you take the difference. You take the difference of each value from the mean, how far away each one is, and you square them and then add them all up, and then divide by the number of numbers, and then take a square root. It's calculated very much like an average, right? So think of this as like the distance from each value from the middle, and then you're dividing by the number of values. Same way you do an average. Now, why the heck do we care about this at all? The reason we care about this is because this is how science works. In science, when we do experiments, we are always taking a sample, right? So for you guys who are doing the Stroop effect, your samples are going to be pretty small. They're going to be, for most of you, it's going to be people who are in your home, right? Could even just be, the sample could just be you, right? And you're hoping, and that's a smaller portion of the entire population of like all people or all teenagers or, you know, all parents, right? Whatever this larger population is. You are exploring just the subset of individuals. So that's your sample, right? And then eventually we're going to try to use math and probability and statistics to try to make an inference about the larger population. So your smaller population is supposed to, your sample, hopefully is going to represent something about the larger population. So something about the Stroop effect. So for you guys doing stuff on the Stroop effect, you know, hopefully the data that you did on 15-year-olds, maybe that does, you know, hopefully it does represent to some extent what 15-year-olds are like in the world, in the US or in New York or in the world, right? So when you take these samples aren't the exact same thing as the population, and so we're trying to guess that, we're hoping that the average here is going to represent the average here. So for example, let's say I wanted to find the average height of women in America. And I go out and I properly collect a random sample of women and women's heights. If I sample properly, usually my results will end up on this kind of a bell curve situation. What that means is, so this is a histogram. This is not like a graph of an experiment. This is a histogram, which means that these are the heights of women, and this is how many women I found at each height, right? And this bell curve, this normal distribution, is when the middle of the data, the mean and the median and the mode are all the same. The mode is where it's highest, right? And the mean and median are mathematical ways we're determining the middle here, right? So they're both the most number of women are 5'5", and also the average, also the mean and median heights of women are the same. And then as you get further and further away from the middle, there are fewer and fewer women at each thing. It's like, are there women who are 5 feet tall? Yeah, I know many. I'm related to many of them, but they're fewer. And so that's getting further and further away from our mean. And this is called a normal distribution when we have this shape where it's concentrated in the middle and then kind of tailing off the sides. So that's when our mean, median, mode are all the same. Again, I'm going to give you these slides. So you will have them. You can enjoy them. What's cool about standard deviations, when you calculate it, that's going to actually give you an idea of how wide or skinny your distribution is. So these are both normal distributions. They're both bell curves around the mean. But just because they're middle, they're arranged around the middle, doesn't mean they can also be tightly distributed or widely distributed around that middle. And so if I take my standard deviation of this sample that I found, I'll find, let's say in this sample, my standard deviation is 2 inches. What that means is, on average, any given person that I sampled here, her height was on average about no more than, on average it was 2 inches away from 5'5". And so if I describe this range of the mean plus or minus 1 standard deviation, so if I'm at 1 standard deviation away from my mean, negatively, if a woman is 5'3", then she is 1 standard deviation lower than the average. If she is 5'7", she's 1 standard deviation above the average height. And so sometimes they'll describe these ranges. This is where most of the sample is, right? Exists in this range of within 1 standard deviation of the middle. So if I say the mean plus or minus 1 standard deviation, I mean in this case, I mean the range of 5.3 to 5.7. This is a good approximation of this is where most of my sample exists within this one standard deviation. Because on average, people are this far away from the middle. And so if I say everyone who is this far away or closer, that includes most people. And mathematically, there's actually a rule about this, and I can't derive this. I'm not a stats guy. I'm not a mathematician. But in a perfectly normally distributed set of data, what happens is you can actually predict, and 68% of the data will be within one standard deviation of the mean. 95% of your data will be within 2 standard deviations of the mean, and plus or minus 3 will get almost all of your data. 99.7%. And believe it or not, for my AP Bio class, they have to know this for AP Bio, but this is also how I determine who ends up being mandated in SGI. Because for me, if my class average is 85 and my standard deviation is 10, right? That means that most of my students are between, so it's my standard, so if I have most of my kids got 85 and my standard deviation is 10, that means most of my students, 68% of my students around there, are between 75 and 95, right? And so anyone who got lower than a 75 on that test is not in the larger group of students, like is not within the kind of normal place that the students are. And so that to me tells me that this is a student that maybe needs more support than the average student on that particular exam, right? That's how I use it. So here's the actual way that I want you to use it. And standard deviation is how far each point is away from the mean on average. And the standard deviation, mean plus or minus 1 standard deviation, is about where 68% of the data points are. We're assuming this perfect normal distribution, right? And plus or minus 2 is where 95% of the data points are. And so let's go back to our original classes. They had the exact same average. And the way that I want you to graph your data always, and I've emphasized this in class, maybe it feels like eons ago when we were in like a physical classroom together, and I do miss it. I miss seeing all of you. I don't know if you remember for the ad project, I told you have to always give me the average. You always have to graph the average. The reason is, again, if I had 100 students in this group, then I can't have an individual bar for every student. It'll be madness. It'll be a nightmare. So I'm just going to graph the averages. The problem here is if I graph the average of the AM versus the PM, they have the exact same average. But you guys know that these two groups are different, right? One is more spread apart than the other. The PM group had a crazy range, crazy wide range, really inconsistent scores, and the AM group, they were more tightly grouped. And so what I can do is I can add something called error bars. And if I say here, if we look here, the error bars represent plus or minus standard deviation, that to me means this is telling me where most of the data are here. So this is my average, and this is telling me where most of my data exists in this range, about 68%. Again, this is the exact same average, but it's saying most of my data exists along a much wider range. That to me tells me these data are much further spread apart. You could think about it this way. The distribution looks like this. My error bars are not telling me the range. It's not telling me where every single data point is. It's just saying the vast majority of students scored within this range. And it's saying the vast majority of students scored within this range. And that's literally all I need you to know about standard deviation. And so I will now happily take questions. If you want me to address anything, I'll do that too. Oh, look, and Adrian and Paul are here. Does anyone have any questions about this stuff? You can feel free to type in the chat. I have no idea how clear it was, especially because I can't see any of your faces. I don't know how I'm doing. Okay, I'm going to stop the recording here.